started. So welcome everyone to the third in our Fall Technical Conference 2020 webinar series. Again, as a reminder, please silence your microphones. And if you have a question, just either put it in the chat box, I'll be monitoring, or use the raise hand feature. And at this point, we'll try and save all the questions for the end. We plan to have a lot of time at the end for to address the question. So again, as a reminder about the Fall Technical Conference, it's an annual conference sponsored by the American Society for Quality and the American Statistical Association with these particular divisions. And our goal at the conference is to engage researchers and practitioners in a dialogue that will lead to more effective use of statistics to improve quality and foster innovation. Excuse me, you can find out more at our website here, listed at the bottom. And even though we're not meeting this year because of the pandemic. Hopefully, if all goes well, we plan to meet in person next year. So be sure to save the date. We'll be meeting there in Park City, Utah. And the call for papers is out. Our deadline, there's plenty of time. March 31st, 2021 is the deadline. So here's a list of our topics. A presenter for each talk gets 50% discount on conference registration. Excuse me, to submit an abstract. Simply go to the link here. You can also find a link to submit an abstract there on the homepage of the Fall Technical Conference. So as I mentioned, this is the third in our webinar series. Today we'll be hearing from Dr. Nathaniel Stevens at the University of Waterloo on his award-winning paper on design analysis of confirmation experiments, joint work with Christine Anderson Cook. Be sure to come back for the remaining talks. We try and usually have them every week. We're going to be, of course, skipping next week because of the Thanksgiving holiday break here in the US. So be sure to join us again on December 4th, where we'll hear from Qingyu Yang, winner of the Wilcoxon Award. But today we're going to hear from the 2020 Lloyd S. Nelson Award winner. This award is given out annually for an article of greatest immediate impact to practitioners published in the previous year's issues of the Journal of Quality Technology. So this year it was the 2019 issues. And the winning article is made available for open access at this link here. Just go to asq.org, look for the JQT publication area. We'd like to thank the award committee. Myself was chair this time around, Stephanie DeHart and David Edwards for the selection, and of course this year's award winner. Award-winning paper is Design and Analysis of Confirmation Experiments by Dr. Nathaniel Stevens and Dr. Christine Anderson Cook. As a brief introduction to Dr. Nathaniel Stevens, he's currently an assistant professor at the University of Waterloo. Prior to that, he was an assistant professor at the University of San Francisco and also served as director of their bachelor's program for data science. He says that his research interests lie at the boundary between data science and industrial statistics. And so his interests are kind of in design of experiments, process control, comparison of measurement systems, surveillance networks. We're happy to hear from him today, and we look forward to what he has to share with us. So at this point, I'll transition over to you.
All right, thank you very much, Caleb. Let me get my screen sharing. All right. Okay, I think you should hopefully be able to see that. All right, well, thank you for that introduction, Caleb. I want to thank everyone who organized this, Mickey and Sarah, Caleb, and everyone else involved. I'm really happy to be here. And thank you to everyone who's tuning in right now or who may be watching this video later in a recording. Thank you for your interest and your attention. Okay, oops. So Caleb already mentioned, but I just want to reiterate that this is joint work with my co-author, Christine Anderson Cook, who I'm sure many of you know, and she's a research scientist at Los Alamos National Lab. So this was a really fun project that I think both of us enjoyed very much, and I'm excited to be here to present it to you. But before getting too far, I want to spend a minute or so acknowledging Lloyd Nelson, the person who this award is named after. And for any of you who don't know who he was, I want to spend a few minutes talking about his impact and his legacy. So Dr. Nelson was trained as an inorganic chemist, received his PhD in 1950 from the University of Connecticut, but soon after he found a passion for statistics and quality improvement, and this led to a long career in applied statistics and quality control at GE for almost 30 years, and then later at the Nashua Corporation for about 12 years. Dr. Nelson made significant contributions to the quality field, even outside of these companies. For example, in the 1960s, he was the editor of the ASQ magazine, then called Quality Control, and it was in this time that he advocated that it be split into two publications, which we now know is Quality Progress and JQT. So we really have him to thank for these two publications. And in fact, he was the founding editor of JQT, a journal that he envisioned would be very practitioner focused, a journal whose articles would offer practical solutions to real problems. And he embodied that philosophy even after his editorship. He wrote for a JQT technical column for almost 30 years. And so for this and his many other contributions throughout his career to the quality field, he received many prestigious recognitions, including being elected an ASQ Fellow. He received the Schuhart Medal, he received the ASQ Distinguished Service Medal, and he was also named an ASQ honorary member. And now, unfortunately, neither myself nor Christine knew Dr. Nelson, but I know I speak for both of us when I say that we're very honored to receive this award. It's a tremendous honor, and to know that our work is perceived as having practical impact and as work that he would have valued really means a lot. So I want to thank the selections committee for this honor. Okay, so getting into what it was that won this award, I want to talk about the problem initially. I'll introduce you to the idea of confirmation experiments if you're not familiar with them, and talk about the need for why we would want to do these things. I'll quickly discuss available methods for designing and analyzing confirmation experiments, but point out some deficiencies that we intend to overcome with our proposed approach to confirmation experiments. We'll quickly go through an example and then end with a summary. And then hopefully there should be time at the end for questions. And Christine is on the line. She's going to join in for the Q&A hopefully there will be a Q&A and discussion. So we'll all be there to chat then. Okay, so the problem, what is the context here? The context is response surface optimization. And I'm sure many of you are familiar with it. In case there are those of you who aren't, I will quickly provide an overview of this context. And so that is that we have a response variable and then one or more factors that we believe will influence that response. And ultimately, we want to characterize the relationship between them for purposes of response optimization. And so you see a picture here on the right-hand side of the screen, and that's of this function f, this unknown function f that represents the true underlying relationship between y and in this case, two x's. And it's this unknown relationship that we're going to try to learn about through a sequence of designed experiments. We're going to experiment with specific combinations of those x's, observe the response, and then fit models to try to approximate this underlying true response surface for the purposes of response optimization. So for example, we may want to determine which combination of the x's maximize the response or minimize it or hold it on target, whatever the situation calls for, whatever your primary goal is. But the underlying goal here is this response optimization. So we're going to search through this region of operability, all the possible values of the x's that are permissible and practically feasible, and try to figure out which combination optimize that response. And we do that within this framework of response surface methodology, which I'm sure many of you are aware of it, but if you're not, we sort of think of this as a collection of statistical tools and techniques that are used for process and product optimization. And it's typically a sequence or a series of phases of experiments to meet this goal of optimizing a response. So initially, we care about factor screening, and here the idea is that we have potentially many factors that might influence this response, and we want to figure out which ones are the quote unquote active factors, the ones that significantly influence the response. And so we typically do that with screening designs and fitting first order response surface models to understand who the important players are. And so imagine for purposes of visualization that we just have two active factors. So say we have some sort of a two-level design with which we figure out that these are the two active ones. Maybe there are a whole bunch that have already been identified as not being active. And so we can disregard those and just carry forward with X1 and X2. So we know they're the important ones. We know where we want to get to, which is to figure out what combination of X1, X2, where in this rectangle, so this rectangle here represents our region of operability. We want to find where in here, which coordinates correspond to an optimized response. And so we might do that with the general sequence of experiments or experimentation within RSM is to start with your factor screening and then start to move in general toward the optimum. We know that eventually we're going to try to pinpoint it precisely, but we're going to try to get there in a little bit more roughly, at least first. So first thing you might want to do is make sure that you didn't start in the vicinity of the optimum. So you might do a center point run here, detect or do a test for quadratic curvature, and suppose we didn't find it, so we aren't in the vicinity of the optimum. So we do a path of steepest ascent or descent. We find that when we get to this point, we can't improve the response any further by going any further in this direction. So we double check again whether we're in the vicinity of the optimum. Perhaps it turns out that we're not, and maybe we're on a ridge, and so we need to take a bit of a pivot and walk in a new direction. Now we get to this point beyond which we have no further improvement. So let's check again for curvature, and suppose we find that there is significant quadratic curvature here. Excuse me. So let's add some more points, maybe do a face-centered central composite design and fit a second order model. So now we are in this phase of, or third phase of RSM, where we're specifically trying to optimize the response. We now think that we know roughly where the optimum is. And so we did these extra points, all of these green ones that you see there. And with those fit a second order surface. And with that second order surface, we've identified this position X that I'll denote by X star as being the location of the optimum. And so that sounds great. You know, we did a handful of experimental runs here. We've identified the coordinates of the factors or the levels of the factors that optimize the response. And then you may ask, what else is there to do? It seems like we did what we set out to do, which was find the optimum and with that be able to predict the optimal response. So what more would we need? Well, you should, the whole key here and the main takeaway is, you know, why would you trust that red point? How certain are you that that is the truth, that that is the optimum? There's a few things at play here. That optimum was found assuming some sort of a model, which may or may not be correct. So that's sort of one source of uncertainty. But then there's also estimation uncertainty associated with sampling variability in that estimate. So how certain are we that this really is the optimum? And that's where this fourth phase of confirmation becomes relevant. What we want to do here is confirm that that is indeed the optimum that we've, or that what we estimate as the optimum is indeed the optimum. So let me formalize this just with a bit of a notation. In that final phase there, we fit this second order response surface model. This linear predictor here with all the betas and the x's, that is our approximation to the unknown function f. And across the whole range of the input space, this is not going to be a good approximation, but Taylor's theorem says that in a localized area, it should be pretty good. So that's sort of the philosophy behind fitting these sorts of models. With that, we fit our estimated response surface, and through that, identified our optimal factor settings, which we're calling X star. And then we can plug those back into this equation, and we get our predicted response. So what we want to do with the confirmation phase is effectively two things. We want to confirm that what we believe is the optimum, X star, we want to confirm that that seems to be true. And I'll talk in a minute about why we want to do that. But to preface that, I'll go back to this picture. And one thing that I think we should acknowledge is that it's very unlikely that that red point, X star, will just happen to be one of the points that we explored in an experiment. It's very unlikely that it is an actual design point, meaning we don't actually have response observations at that position. All we have is a prediction from a model. And so we want to, in some sense, confirm whether or not that that prediction is reasonable. So we want to determine whether that position is indeed the optimum, and we would also like to reproduce the good performance that we saw in the experiment in terms of that predicted response. And so there are a number of reasons why you might want to do this. One very practical one is that often there is a lapse in time between when your response surface design is conducted and when you take your optimum and put those results into practice. And it would be nice to confirm that there's no significant deviation in those results that arises over time. As well, these sorts of experiments are often done in a different environment from the ordinary process. It might have, the response surface experiment might have happened in a laboratory or on a prototype of your process. Or if you're in a manufacturing process, the experiment might have been done in the downtime. And so the question then is, does these results and this good performance, does that carry over to the ordinary process? And so that would be another reason maybe that you want to confirm things. And then the final one, the point is the one that I already made, that we're effectively, when we identified that red dot, we're relying heavily on the belief that that model accurately reflected the true underlying surface and that there was minimal variability in that estimate. And though neither of those things, both of those things might be true, or one might be true and one might be false, or they might both be false. So it's a good idea to do some confirmation, to try to study what you believe to be the optimum a little bit further. And a lot of people talk about this as being a good idea. If you look in the major design textbooks like Wu and Hamada or Montgomery, they all mention that this is something we should be doing, but unfortunately they provide very little specific guidance in terms of both the design and the analysis. They say that it's a good idea to confirm your optimum, but don't say much more than that. And so it begs the question, what should we do to confirm the results of the fitted response surface? In particular, what data should we collect and how should we analyze that data? And the lack of guidance from the statistical community has basically resulted in an enormous amount of variation in how practitioners are actually doing these confirmation experiments, if they're doing them at all. And so Christine and I did a literature review where we looked at a whole bunch of published response surface studies where scientists were publishing the results of their experiments. And what we found was that there is really no standard approach to either the design or the analysis. One thing that is common is that these confirmation experiments tend to use one or more runs somewhere in the design space, but there's no consistency in terms of how many runs to use and where to put them in the design space. So I think that we as the statistics community need to help out there. And then on the analysis side, very often the analysis is informal and guided by practitioner and context expertise. So what you might imagine is that they take a few, say 3 confirmation observations at a single location, and then compare the average of those response measurements to the model's predicted response at that same location. And then they compare these two numbers and use context expertise and relevant judgment from their domain to say, are these things similar or are they different? Are they close enough or are they really far apart? And that's the kind of decision process that is made. And the one notable exception to a lack of guidance was a really nice paper by Willis Jensen in JQT in 2016, where he recognized this as a big problem. And there's a big gap between the literature and what's going on in practice. And so he came up with a framework for both the design and the analysis. And what he recommended was running a number of confirmation runs at what you perceive to be the optimal factor settings. So at this X star. And he recommended something in the neighborhood of 5 to 10 confirmation runs. And you may or may not look at those numbers and think, wow, those are really small. But what we need to acknowledge here is that this confirmation experiment comes at the end of a potentially very long experimental journey, and there's often not very many resources left over at the end. And even convincing practitioners that this confirmation phase is something they should do and set aside resources for is often difficult. So these numbers may seem small, but I think it is quite realistic that there's not a lot of money or time or resources left over to do much more than this. So his recommendation was to do 5 to 10 confirmation runs at the predicted optimum, and then compare these new response observations either individually or in aggregate to a prediction interval calculated based on your response surface design for the response at that location. And I want to reiterate the importance of studying this optimal setting further. And I think that what Willis acknowledges by recommending all of these confirmation runs at this estimated optimum is the fact that we probably don't have any real response observations there yet. All we have is a prediction for that response. And so designing the experiment in this way gives us some information about that location and what response you might expect from it. And so the comparison kind of goes like this. You could either take an average of those confirmation observations and look at whether it lies in the prediction interval for the response at that location, or you could calculate a prediction interval, a simultaneous one that accounts for multiple comparison, and then check whether each of those confirmation observations lie in that interval. So effectively, what this approach is doing is it's determining whether at that estimated optimum, whether there's a significant difference between what your model predicts and what you've actually observed in your confirmation runs. And so it's a very sensible thing to do and a very sensible way of going about it. But what happens if our understanding of that location is incorrect? We acknowledge that our understanding of X star is based on this model. What if that model wasn't a good characterization of the underlying response surface? In which case, the true optimum might be close to our current belief, our X star, but it might be somewhat removed. So what if that's the case? By putting all of your runs at a single location, you're not gaining any information to help determine whether this problem may be occurring. And then additionally, the motivation, I think, of making this decision based on prediction intervals and the like was to remove the somewhat subjective nature of the decision process that appears to be going on in the literature, and to sort of formalize it in some way. However, what if you did want to account for that subject matter expertise? What if you felt like that was something relevant that you wanted to incorporate in your analysis? The approach proposed by Willis doesn't do that at the moment. And so those are the two main deficiencies as we see them, and they are the things that our proposed methodology has been designed to overcome. So speaking of design, we'll start there and then we'll talk about the analysis. So we're going to imagine that we've got this overall budget of n confirmation runs, acknowledging again that typically this is going to be a small number. It might be nice to think about determining this number through some power analysis, but the reality is that this is probably some fixed number determined by resource constraints. So within that, we need to figure out how to sensibly use that budget. And so we agree that studying that optimum is a good thing to do because, again, we probably don't have response observations there. All we have is a prediction there. So we should try to observe the response at that location. So what we recommend, though, is putting some of our runs there, but not all of them. The remaining runs, we basically suggest sprinkling around that in the pursuit of exploration around that, acknowledging that X star may not be the true optimum. It might be close, but there might be something nearby that's even better. And I say sprinkling, I don't mean that in a haphazard way. What we recommend is uniformly dispersing those remaining confirmation runs in accordance with an equiradial design. So what that means is basically uniformly spreading out those points around the surface of a hypersphere centered at that estimated optimum. So here's a few graphical illustrations just to give you a sort of a visual intuition. So here we're imagining, again, that we have just two factors, and our budget here is 6 confirmation runs. So in the paradigm that we're suggesting, we have a few options here. We could choose to put 3 runs at the estimated optimum and put the remaining 3 around the surface of the hypersphere, which in this case is a circle. Or we could do 2 at the optimum and 4 around the circle, or 1 at the optimum and 5 around the circle. And then the question that arises here then is, which of these choices is the best? And I don't think there's any one right answer to that question. And instead, there are trade-offs that you need to think through in making a decision like this. For example, in this leftmost scenario, we're putting 3 replicates at that estimated optimum, meaning that we're getting a decent amount of information at that location. And that replication allows for an estimate of the variability in the response. However, it leaves relatively little exploration outside around this, this circle. Whereas on the other extreme, here on the right-hand plot, by putting just a single run at the estimated optimum, we're not getting relatively as much information about that location, but we are doing a little bit more exploration by doing just one here. That's afforded us more points around the perimeter of this circle. And so these are the sorts of trade-offs that a practitioner would want to think through when they're thinking about designing this confirmation experiment. So the following choices then need to be made within this way of thinking about dispersing your runs, some at the middle versus some to the around the perimeter. First of all, we need to know what capital N is. As I mentioned, that's typically driven by resource constraints. We then need to think about how to allocate the runs, how many to put at the estimated optimum versus how many to put around the perimeter of your hypersphere. And as we just talked about, there are several practical trade-offs that need to be considered. But subject to those 2 decisions being made, a third one that we need to consider is the radius of that hypersphere. That again is going to be a choice of the user. And there's 2 things that we see as being big drivers in this decision. One is, where is X star in relation to that region of the operability? Is it nicely in the middle, or is it near an edge or a corner? Because if it's near an edge or in a corner, depending on the radius of your hypersphere, some of those points will lie outside of the region of operability. So you need to take that into account when you're thinking about the radius. Something else that might inform the radius is your uncertainty in the estimate of the location of X star. You could, using your response surface design and the data and the model that came out of that, construct a confidence region for that optimum. And so that would be a region where you'd be reasonably confident that the optimum could be anywhere in there. And so that might guide your choice of R, so that your equiradial points are somewhere within that region that you would not be surprised to find the optimum. So choosing R is another choice that needs to be made. And then lastly, subject to all of these other choices, you need to decide where to put the equiradial runs around the perimeter of that hypersphere. If we think back to those polygons that I had just had on the screen a moment ago, you could rotate those in at any angle, and that preserves the equiradial properties. So the question is, which rotation is the one you should choose? And that may be guided by your understanding of the region of operability. Maybe there are areas in that region that are practically feasible, but for some reason undesirable. So you want to avoid them. And so maybe that factors into this 4th decision. But whatever the case, just know that within this sort of a design, you've got these 4 choices that need to be made. So what we recommend, subject to the idea that more is obviously better, but at a minimum, we think that there should be 6 confirmation runs where you put 3 at the optimum, and then the remaining ones dispersed around the surface of your hypersphere in this equiradial fashion. And so what this does basically is it balances gaining information at what we currently believe the best choice of the factor levels are. It gives us information at this estimated optimum. And it balances that with doing a bit of gentle exploration in its vicinity in case we're not right about the location of the optimum. And now one challenge that I want to acknowledge is that finding an equiradial design is trivial in 2 dimensions. You can just look at a circle and scatter as many points as you want to in an equiradial way there, but it becomes non-trivial in higher dimensions, even as small as 3 dimensions on a sphere. The idea of finding an exact equiradial design is an unsolved problem. And so there are algorithmic ways that you can find approximate equiradial designs, but they can be computationally intensive and still at the end of the day only approximate. So that's potentially one avenue of further research that could be explored. So that's the design. So imagine that that's what we've done. We've got some points scattered around in a hypersphere, and then we've got a couple replicates at our current estimated optimum. So what do we do next? How do we estimate this data? Or sorry, how do we analyze this data? And so we propose doing this through a comparative probability metric framework, where the goal, just like Willis's goal, was to formalize the comparison of the confirmation results with the optimum predicted by the previous experiment, but where we're formally and explicitly going to incorporate the practitioner input concerning what difference is considered practically meaningful. Thinking back, and I'll remind you that the way practitioners typically analyze these experiments now is that they have an estimate of the response at a given location based on their confirmation runs, and then they also have a prediction of that response at that location based on a model. And they just take those 2 numbers and they look at them and they say, are these close enough? And if the answer is yes, then they consider the confirmation experiment a success. And if not, then they consider maybe success and failure is not the right way to phrase it. But if it's a failure, then they realize maybe there's some more refining we need to do in terms of our understanding of where the optimum is. So in that comparison, as crude as it is, they have some understanding of what constitutes a practically important difference. And so we're going to call that delta. So we're going to define delta to be this number bigger than 0, such that absolute differences in responses less than this threshold would be considered practically negligible. So what that means is that if you have 2 response observations lying within plus or minus delta of one another, then they would be considered practically equivalent. And we think that this understanding, this definition of delta and what constitutes a practically important difference should be incorporated into the analysis, especially in this day and age when there's this outcry against p-values and statistical significance when they've been prioritized at the exclusion of practical significance. I think the time is now to think about things in this way, to not discount this practitioner input and to explicitly incorporate it in the analysis. So what our comparative probability metrics do is quantify in practical terms the probability or the likelihood that your confirmation results agree with your response surface results, or at least that they're not worse. So let's formalize that. I'm gonna take a drink of water though. Okay. So just reminding you of the notation and what we have, we've got at a given location X, we want to compare the estimate of the response surface based on 2 things. We have an estimate based on our model, and then we have an estimate based on our observations from the confirmation experiment. And so what we want to do is sort of characterize the difference between them, and what is currently done is just to look at that difference and ask, how big is it? Is it big enough to matter or not? That's how people presently do it. But that comparison is crude and inappropriate because it ignores all of the uncertainty associated with estimating your response surface model, and also the variability associated with these confirmation observations. So what this comparison is missing is accounting for that uncertainty. It's missing the notion of, how likely is it, given all of my information, that I would have observed a difference that lies in this interval I need it to. And that is precisely what our metrics are intending to quantify, the probability that a difference would be practically important or not. And so we have two in particular that we consider. The first is the probability of agreement, which has been used widely in a variety of areas as, in general, a way of quantifying the similarity between two groups, and while accounting for what difference between those two groups would be practically important. So in this context, the statement of that probability is, what's the probability that the difference between these two estimates of the response surface are within plus and minus delta of each other, where this plus and minus delta range represents basically a range of practically negligible differences. Now, this particular metric, and I'll talk about the second one in a moment, this one is particularly useful if your goal of RSM was to hold your response on target, to figure out which values of your factors, which levels of the factors would keep your response operating within some tolerance that is acceptable. Now, that is a useful RSM endeavor and a useful way of thinking about optimization, but arguably the more common applications of RSM is for purposes of maximization or minimization. And so for that, we have something that we call the commensurate probability. And so what this acknowledges is that if in your confirmation experiment, you got a result that was better than what you had predicted from your response surface model, that wouldn't be upsetting to you. You would be quite happy to find that your prediction was an under prediction in terms of good performance. You'd be totally happy if your confirmation results were better than what you had predicted with that model. And so the commensurate probability is defined with that in mind. This idea that I don't actually care if my difference between what was observed and what was predicted is within some tolerance. I want to know if it's, maybe a little bit worse, practically not worse, but maybe the confirmation results are numerically worse than what is predicted by the model. But as long as it's not practically worse, then that's fine. But then you have this whole other tail, which is where it's better. And the commensurate probability is designed and defined to quantify the likelihood that would happen. So when you care about response maximization, we define the probability in this way: the probability that this difference would be bigger than negative delta. So that's accounting for the chance that, or rather the scenario that your confirmation runs are a little bit worse, but not so worse that you would say it's inferior. It's within that tolerance of practical equivalence. So what's the probability of being bigger than this negative delta? So being effectively, this is like a probability of practical non-inferiority. And if what you care about was response minimization, we just flipped the inequality and the sign on delta because the direction of the comparison changes. But broadly speaking, we've got the probability of agreement and we've got the commensurate probability. And we use these as a way of determining how agreeable or how much better, or at least not worse, your confirmation results are relative to what was predicted from your response surface experiment. In terms of calculating these probabilities, it's very straightforward. It boils down to basically standard normal probability calculations based on the usual distributional assumptions that we make with these second order response surface models. So for example, the one that you see here is the typical one where we make typical OLS assumptions. Now we assume a separate model for our confirmation runs. We obviously don't have enough information to estimate all these betas and things like that. It would be nice if we did, but we don't. So we just assume that, again, we have a normal response at this location. We're allowing both the mean and the variance of those response to differ from the mean and the variance in the original response surface experiment, basically acknowledging that these things don't need to be the same. And the whole goal is to quantify how different they might be. So within the confines of those distributional assumptions, these, as I said, just work out to be standard normal probability calculations. So nothing too fancy going on here. The estimates of these probabilities we find by plugging in estimates of all of our parameters. So the mu's and the sigmas we estimate with the betas in the original the model, and then estimates of the variance and the mean in our confirmation runs. And so we just plug these estimates into these equations, and we get our estimate of either the probability of agreement or the commensurate probability, as the case may be. So a few remarks. The first is that I haven't said yet how someone makes a decision. I've said how we might quantify or help inform that decision by calculating one of these probability metrics. But ultimately, the decision as to whether your confirmation is successful, whether in some sense you've confirmed what you found previously in your response surface experiment, we leave this up to the users. They're going to then look at these probability estimates, and it's up to them to decide if they're big enough or small enough to be convinced that the confirmation was a success or a failure. So for example, if your probability of agreement is 0.8, is that high enough for you to be confident saying that your confirmation results agree with your predicted model? Maybe it is, maybe it's not. That's up to you to decide as the practitioner. I haven't said anything about it until now, but we also accompany these estimates with confidence intervals. We use a parametric bootstrap in order to calculate these confidence intervals. If you want more details about that, you can find it in the paper. One thing we need to acknowledge, though, is that the number of confirmation runs at a given location is typically going to be small, and particularly in our recommendation of the design, in the equiradial approach, those equiradial points around the surface of your hypersphere, there's no replication there. NC is equal to 1. So at those locations, you have no estimate of sigma c, the variability in the confirmation experiment. And so if you look back at those, the formulae that I showed for calculating these probabilities, they relied on an estimate of sigma c. So if you don't have that, or you worry that it's imprecisely estimated because of a lack of substantial replication, then you may choose to instead use sigma hat as estimated from your original experiment. And I don't think it's too big a leap to make that assumption if you need to, but that is a practical approach to dealing with this situation. And then the last thing that I want to make clear, and I want to make this to be really clear, is that we don't need normality here. Normality makes those probabilities very straightforward to calculate, but the underlying philosophy of the probability of agreement and commensurate probability have nothing to do with normality. This idea of quantifying that difference and asking whether it's practically important doesn't rely at all on the normality. You could use other models, generalized linear models, whatever you want. Change up your distributional assumptions if that's appropriate. You need to acknowledge that the computation and calculation of these probabilities is going to be complicated now, but they will still work. They're still defined and interpreted in exactly the same way. So I think that that's valuable. So let me just quickly talk through some of the advantages as we see it relative to existing approaches. First, relative to the predictional interval approach proposed by Willis, what we see as an advantage of our approach relative to that is that we are emphasizing the practical importance and practitioner input into this decision. We're formalizing it. So I think doing something better than what is currently done, where the comparison is very crude and ignores uncertainty. We now account for that and we formalize it in that sense, but we're still incorporating that input. And I think that that's a really valuable thing to do. And the ability, at any number of these stages that I've been talking through, I've been many times restating that there are choices that a practitioner is going to have to make. And so what that facilitates is a very, or it can allow for a very tailored approach based on whatever context a practitioner may be dealing with. And then the last point here that I see as an advantage is that, in my opinion, this is very intuitive. It's very easy to interpret. It's very much like what practitioners already do, with a slight tweak that that makes it more appropriate. And so I think there's value in the fact that it's quite intuitive and straightforward to understand. Okay, so putting all of this together, our recommendation for the design is that, as accounting for resource constraints, we're recommending do an equiradial design centered at the estimated optimum, where you have a bit of replication at that center point. And that's balancing, as we said, gaining information about that optimum, which you may not have had before, with doing a bit of exploration around that optimum in case it's incorrect. And then our analysis is basically to compare your confirmation results with what's predicted by your response surface model using a probability of agreement or commensurate probability. And the nice thing about that is that we are incorporating for practitioner input, while still formalizing the comparison, accounting for uncertainty in it. Okay, so that's the approach that we're proposing. And I'm going to go through an example now. Let's see how I'm doing on time. Decent. And so what this example is going to do is to illustrate how you might analyze a confirmation experiment with these probabilities. This example comes from the literature, but that means that it was published before we proposed this equiradial design approach. So that hasn't been done, but we'll talk about what insights might have been gained had they done that. So the example comes from the field of molecular science. The investigators were looking at optimizing an enzymolysis for purposes of preparing peanut antioxidant hydrolysate. And the goal here was to maximize something called DPPH free radical scavenging rate. And there were 4 factors that the investigators thought influenced this response. And through a 29-run Box-Benken design, they fit the following second order response surface. And with this response surface, they identified that the optimal factor levels were x1 equal to 150, x2 equal to 62, x3 equal to 25, and x4 equal to 8.5. And they found that at that optimum, their model predicted the response to be 0.9142, and then we've got the 95% prediction interval shown there as well. Now they were wisely did a confirmation experiment. They wanted to validate that predicted response. So they did 3 confirmation runs at that optimum, and that optimum, this configuration of the factor levels that you see here, was not one that was studied in their previous experimentation. So they did 3 confirmation runs there. And what they found was that based on those runs, they estimated the optimum they estimated the response to be 0.9006 with a margin of error of 0.0012. And so if you look at this number, 0.9006, it's smaller than 0.9142. So strictly speaking, the confirmation runs suggest that the optimal response is slightly smaller than what was predicted by the model. And if we look at if we were to do the Jensen approach, we would take this average and check whether it lies in that prediction interval, and it does. So by that mechanism, we would conclude that despite this being slightly inferior, it's still, it's fine. It confirms the the confirmation was a success. And the authors didn't do that approach, but they came up with the same decision. What they said was 0.9006, yes, it's slightly worse than what we predicted, but it's not that bad. It's close enough that we believe these results are a success. And what they defined as close enough was that it was within 2% of that predicted optimum. And so this is a perfect opportunity for us with our probability metrics to quantify what is the likelihood that this would happen, that this difference would be within 2%. So just to reiterate, the authors concluded that because that there was sufficient agreement because the difference between their average from the confirmation runs and what was predicted by the model was within plus or minus 0.018284. And that's 2% of their predicted optimum. So we could come along now and say, well, let's just define that as our delta and calculate the probability of agreement. What's the probability that that difference would be in that tolerable range? And so if we do that, we get an estimate of 0.5129 and a lower 95% confidence bound of 0.0763. And so, yes, it's true that this difference was within 2%, and they deemed that as a success. But the chances that that would happen are only 0.51. It's not very high, and that lower bound on the confidence interval suggests that the agreement could be even much lower than that. And what this is reflecting is, or what we're accounting for in this number, is the uncertainty associated with estimating that response surface model, and then also the variation in the confirmation observations. When you account for those, you become much less certain that the difference really is within plus or minus 2% of one another. So, and I should just pause for a second to state that this is in contrast. This kind of contradicts the other analysis methods. I think that if I was looking at this number, would come up with a different conclusion. Now, we could also go one step further and calculate the commensurate probability. That is a reasonable thing to do here, because the authors compared about maximizing their response. And we know, based on this tolerance delta, that as long as the difference is bigger than 0.018284, then the investigators would be happy. So, and if that were the case, these confirmation results would be classified as practically non-inferior. So we could ask, what's the probability of that, and quantify that with the commensurate probability, which we estimate to be 0.58 roughly, with a lower bound of 0.018 roughly. And so these reasonably small values and this low confidence limit suggest that it's actually quite likely that the observed confirmation results are practically inferior to what is predicted by the estimated response surface. And so you may see that and say, okay, well, that may signal to us then that what we predicted with our model is just not as good as what we're going to see in real life. And maybe that's the case, and maybe that's fine. And maybe, though, we still are correct in our understanding of the optimum. X star is the optimum. We're just not going to get as good performance in real life as we got in that experiment. That's one possibility. Another possibility is that we just didn't find the optimum correctly. We're maybe nearby, but there's something that could be slightly better, in its neighborhood. And unfortunately, with exploring only that optimum, you gain no additional information to help answer these questions and elucidate whether we have found the optimum and we're just getting suboptimal performance in real life, or maybe we missed the optimum altogether. So had the authors done what we propose, which is this equiradial design centered at the optimum with some replication there, they would be able to address these issues. And if they did that, and perhaps you find on that equiradial runs, maybe some of them perform better than the optimum, your current estimate of the optimum. And if that's the case, then that might suggest to you to do a little bit more exploration, maybe even consider a few more design points, enough so that you would fit another second order model in that new neighborhood to get a refined understanding of the optimum. But what's clear here with this example is that you really don't have enough information to make any of these decisions with any kind of clarity without exploring beyond that estimated optimum. Okay, so that I'm effectively done. Let me just quickly summarize some points here. The confirmation experiments are important and they should be performed. That I hope is clear. And there's been relatively, until recently, little guidance in the literature for how to actually do this. Willis-Jensen proposes a very nice methodology, but what we propose is something that we feel explores the space a little bit more with this idea of balancing exploration at our current guess as the optimum versus exploring the neighborhood around it in case that guess is wrong. And we also incorporate explicitly practitioner information. These probability metrics account for the context expertise that tells you what difference is acceptable and what difference is unacceptable. And we formally incorporate that. And I will stop there. And I think we still have a few minutes for questions.
Yes, we do. We got about 5 minutes left. Thank you, Nathaniel. That was a great talk. We do have some questions that have already come in, but I'll start off with a comment from Willis-Jensen himself, who said that he just wants to add that the goal of his paper was to start a conversation and encourage brighter and smarter individuals than himself to do some work in the area. So in his mind, mission accomplished. And he's glad to see excellent work building off simpler initial efforts. So the first question I've got here is from Steve Gilmore, and he asks, are the CPMs Bayesian, i.e. subjective probabilities?
That's a good question. In our paper, they were not. We were calculating them based on the estimators of the response surface. And so that, I guess, has some advantages and disadvantages. You could come at this from a Bayesian perspective. That might give you a bit clearer an interpretation that what the probability that you're calculating really is a difference between parameters. But we felt the frequentist approach here was more appropriate and a more natural extension of what practitioners are already doing, which is comparing these estimates. So we felt that the frequentist approach to quantifying that probability was the right answer. But if you look in the literature, there's been many papers about Bayesian versions of the probability of agreement that you could easily adapt to this situation if you felt that that was what you wanted to do.
Now we've got a question here from Keith Toby, I believe pronouncing that correctly, hopefully. He says, you use several terms from non-inferiority testing or equivalence margins, but don't seem to use the same method such as TOST. Is the method really just non-inferiority, or is it, or what's the difference, if there is?
That's an excellent question. So there is a very big similarity between what we propose with these, the probability of agreement and equivalence testing and non-inferiority testing. And the similarity, I think, is the philosophy, that you don't want to begin necessarily with the assumption that two things are the same and then look for evidence that they're different. We instead start with this assumption that they're different and look for evidence that they're the same. And then this idea of practical equivalence is central to that. So in that respect, two-sided t-tests and all of the various equivalence and non-inferiority tests, we share that in what we do with this probability approach. But the big difference is that we're not at all doing hypothesis testing. Our focus is on estimation of this probability. We're not concerned about p-values. We make a concerted effort to move away from that and to not do hypothesis testing. It may still be equivalence testing, but people already struggle with p-values. That's not going to change whether it's a traditional hypothesis test or an equivalence test. So we've moved entirely away from that and focus explicitly on estimating these probabilities. But the similarities are intentional. We drew from the philosophy of equivalence testing when developing these things.
I think we've got time for this one last question here. It's another one from Steve Gilmore, and he was asking if you had told the audience how to choose the radius. I think you had discussed that at sort of a high level, but if you wanted to talk about it again.
Yeah, so I didn't say explicitly. I should have put a picture. We have a picture in the paper where the idea of using the confidence region of the location of the estimated optimum is a really helpful way of looking at it, because that gives you sort of a region within which you'd be pretty, you'd be unsurprised to find the optimum in there. And just like any confidence interval, we may have an estimate, but we know that's probably not the true value of the parameter. The true value, though, we think is somewhere in that interval. So if we use that same way of thinking about a confidence region for that location of the optimum, you could choose the radius of your hypersphere to kind of fit or fill in that confidence region. So you're exploring it in a little bit more depth than what you have at the moment of its calculation back in the response surface experiment.
Okay. So I think that's all the time we have for questions. Thank you again, Nathaniel. That was an excellent talk. And just as a reminder, we'll have a recording of this talk up on the Fall Technical Conference website. You'll see the FTC webinars tab. Go there and look for Nathaniel's abstract. It'll be right beneath there, a link to the YouTube recording. And you could click on the title, and that will get you access to his slides. So expect that probably about a day or two. So thank you again, everyone. And be
Thank
sure
you,
to
everyone.
join us next time.